Hello, AP Calculus BC students, and welcome to your last AP targeted review on the dreaded power series. Question 6 on your BC free responses is almost always a power series. That's been true for the last couple decades now. And on one hand, I understand that that seems intimidating, but on the other hand, that really makes the AP exam pretty predictable. You're like, okay, question 6, that is 1/6 of the points from my free responses are going to come from a power series. So if you really heavily study that, you've got like a sixth of the exam, right? 12 something percent in the bag. And that's awesome. So what do you actually have to do on these power series questions? Well, I took some time to put together kind of two free responses that are really an amalgamation of many different free responses, and they kind of introduce more and more functions just so I could make sure you covered everything you need to know how to do. The first thing you need is, of course, to know your 4 essential power series by heart. So can you list out e to the x, sine of x, cosine of x, and 1 over 1 minus x, which is, of course, our geometric power series. And at their core, you also need to be able to build a Taylor or Maclaurin series, right? A Maclaurin series is just a Taylor series, but centered at 0. I used C for the center here, yeah? And you need to be able to build that from scratch. Your usual f of the center over 0 factorial times x minus the center to the 0th, and follow the pattern out for as far as we need. You need to be comfortable differentiating or integrating power series, finding the radius or interval of convergence. That's where we use the ratio test. We'll do that a few times. And the two really scary ones for students, the Lagrange and Alternating Series error bounds. So we are going to cover all of those today. So let's go ahead and take a peek. So here's my first question 6. There are two of these. We have f of x, which is a differentiable function, and you will see the table of values here where it gives you n, and then it gives you the function's derivative for any value of n. So for example, an n of 3 means the third derivative of this unknown function evaluated at 0 is 6/5. And then we have a second Maclaurin series for g of x. And I don't know what this is the Maclaurin series for. Maybe it's ln of x, maybe it's e to the x, I don't know. It's some combo of things. And they told us that the general term is here. And if you sum it all up, they actually were very kind and gave you the first couple terms, and then again gave you the general term at the end. So let's jump into this. The first thing they're going to ask us to do is to do the 4th degree Maclaurin series p sub 4 of x for f of x. So they're saying we have this unknown function f of x. We're going to write a series that approximates that function out to the 4th degree, right? That p sub 4 doesn't mean write 4 terms. It means go out until you hit the 4th power. So we're going to start with our basic f of 0 over 0 factorial times x minus 0 to the 0th. And we're doing this 0 for these two spots because they told us it's the Maclaurin series, which is always centered at 0. If they had centered it somewhere else, you'd change those two purple zeros to wherever you were centered at. And then we have our f prime of 0 over 1 factorial times x minus 0 to the 1st. And we're going to go out to the 4th power. This would be a 1st degree Maclaurin approximation. So let's do a few more. So we have f double prime of 0 over 2 factorial times x minus 0 squared, 3rd, and we of course need one more. And you could use Roman numerals here, but it's pretty common to just, after 3, just switch to the 4 in parentheses like this to show it's the 4th derivative. 4 factorial x minus 0 to the 4th. And I'm glad we're only going out to the 4th because I ran out of room. And then from here, it's just a matter of course, substituting everything in. And we're going to get all those values from the table up above. And they even told us up here, f of 0 is -1, which I need right now. So -1 over 0 factorial, which is 1. And then I'll reduce this to x to the 0th. Then we have our plus. The first derivative is 2. So 2 over 1 times x to the 1st. Second one is -2. Almost caught that in time. 2 factorial is 2. X squared. Third derivative was that weird 6/5. Who came up with this problem? And then it's over 3 factorial. So I'm just going to rewrite the 3 factorial as 1 over, and then 3 factorial is 6. X to the 3rd. And our 4th derivative is -12. So we'll do -12. And then 4 factorial, I think 6 times 4 is 24, isn't it? Something like that. let's see, 3 factorial, 6, 6 times 4 is 24. Yeah, that seems right. X to the 4th. Okay. Now, the question comes up, how far do you have to simplify? And actually, at this point, you are done. You're required to show a single coefficient for each degree. So, for example, the third degree, the coefficient is 6/5 times 1/6. Right, that is the whole coefficient. It would not have been okay if I said something like 6/5 x cubed plus 1/6 x cubed. I know that's not the same, but you can't do that because you haven't combined your terms. So there is an expectation that you simplify down so that you have a single coefficient for this. However, I'm going to go ahead and go a little bit further. So we have our fourth derivative approximation, and I can use an equal sign here because this is exactly equal to the fourth degree. And x, anything to 0 is 1, so I have -1 plus 2x minus x squared plus 6's cancel, 1/5 x cubed, and then 12 over 24 is 1/2 x to the 4th. We went out to the 4th power. We are good to go. All right, next we have to find or use the ratio test to find r, where r is the radius of convergence, and this is for g of x. So g of x is down here. In order to use the ratio test, we need to know the general term, and that was kindly given to us. The way the ratio test works is it basically says any power series, these are all power series, if you go out infinitely far, behaves like a geometric series. And we know for any two terms in a geometric series, in order for that to converge, when you divide the two terms, they need to be less than 1. Right? The idea, if you had like 1, if I'm multiplying by 2 every time, 8, 16, 32, that's not going to converge because my value I'm multiplying by my r is greater than 1. But if I had 1 and then I multiplied by a half, there's a half, a fourth, an eighth, 16th, eventually that's going to go to 0, right? That sequence converges, and that's because my r is 1/2 every time. That's a value less than 1. And that's what the ratio test does. The ratio test says take two terms, and when you divide the bigger one, or I guess not the bigger, but the next one over the previous one, you better get an answer that's smaller than 1. Now the way we write that out here is we say the limit as n approaches infinity. And we don't care if the radius is positive or negative, so we just say let's just make them all positive, make our life easy. And we have to divide two terms. The two terms we need to divide are the nth term, which we'll say a sub n, and then one further than the nth term, because this property that Taylor series behave like geometric series only works out at infinity. Okay? You could probably do a sub n and a sub n minus 1 if you wanted, but either way they need to be infinitely far. And we're hoping that when we divide these two, we get a ratio that is less than 1. Okay? So I'm going to leave the less than 1 off. We tend to just kind of lead into things here, and we're going to do the limit as n approaches infinity, and we'll tackle these two. I'll do a sub n first because that is our general term which is given to us at the top. -3 to the n minus 1 over n times x to the n. And then we'll do our n plus first term up here. That means wherever you see an n, replace it with n plus 1. Over n plus 1 times x to the n plus 1. Ooh, bad spacing, but we'll make it work. That's a negative on the 3. There we go. Next step is we try to rewrite everything so that it's not a fraction within a fraction. It's not this complex fraction. So maybe I'll treat these as being over 1, make things a little bit easier to see. So the limit as n approaches infinity. You could certainly say, well, if you have applying absolute value, doesn't it turn the -3 into a positive 3? Yeah, you're right. I think we'll find that most of this will cancel out anyways, but you could totally do that if you wanted. I'm going to save it for the end. So generally find we need a pretty long fraction line on this next step, and we have -3 to the n plus 1 minus 1, that's just to the n, okay? And then we have our x to the n plus 1, and then when we multiply by the reciprocal, n times 1, we're going to have an extra n up here. And then in the denominator, we still have this n plus 1. Maybe I should cross things out as we use them, that's probably easier. We have an n plus 1. Okay, we have a -3 to the n minus 1, And if you need this to slow down at all, you really might want to go back to my video on the ratio test, right? We go a lot more in depth of how everything's getting flipped and everything. And then I'm seeing an x to the n here that I need to get rid of as well. Almost always with this ratio test, what should end up happening is you should have one of each type term in the numerator, one of each type term in the denominator, right? I have the -3 numerator, -3 denominator, n numerator, n plus 1, and so on and so forth. Okay. I'm going to go ahead and use our properties of exponents and break this apart a little bit more. So I'll keep my absolute value, and we'll keep the -3 to the n, and then we'll take the x to the n plus 1 and say that's x to the n times x to the first times n. And then while I'm doing this, I might as well group my like terms as well, where I have -3 to the n minus 1, but I'll do -3 to the n and -3 to the negative first, right? So that took care of this guy in the middle here. And then we have an x to the n here, and then we have our n plus 1. Nice. All right, anything we can cancel? I hope so. This is always the fun part where you see, you're like, I hope everything goes away. I'm pretty much done. There's the x to the n's, and we didn't quite get everything. Okay. However, there are two things I'm going to do. Because we're dealing with the limit as n approaches infinity, I really like to group anything with n together in a single fraction. So I see an n and an n plus 1, right? That takes care of these guys. And then anything without that, I like to kind of group on their own. So we had x to the first, which is just x. Then -3 to the negative first, I'm going to bring up to the top and say it's -3 to the positive first power. And I like to do that because then it's a little bit easier to see how the limit's going to apply here, where my limit of n over n plus 1, you think of the coefficients. Plus 1 doesn't matter at infinity, and anything divided by itself, well, actually, that's just 1. So when you finally end up doing the limit, we get 1 from the n over n plus 1 times x times -3, or -3x. Or, of course, if we do the absolute value of -3, to me this is 3 absolute value of x. Now, we don't want to stop here because there's one more step, right? We needed this limit. In order for this series to converge, these two terms need to divide to be a number that is less than what? Less than 1. The radius of convergence is defined as the center is isolated. We don't have any of these coefficients out here. So I'm going to divide both sides by 3, and that's going to give me x, absolute value of x, is less than 1/3. Or if you wanted to show the center, x minus 0 is less than 1/3, right? We can see that the center is 0, and we are allowed to go 1/3, you should capital R, I guess, 1/3 maximum in each direction. So you could use 1/10 as an x value up here, and that would be allowed. But you couldn't use 2/3, we would diverge at that point. And honestly, when I was going through and doing my solutions here, I was like, oh, I should probably check and make sure that I'm right. And so I just made a quick graph, and I'll show you how to check it on Desmos. It's really fast. Of course, you won't have Desmos or even a graphing calculator on your desk, but a lot of this is why. Because if they ask you for the radius of convergence, you just type in your summation. You'll notice that I used b up at the top here. My cursor going. I used b at the top because it's 1 to infinity technically. I just set b to go from 1 to 100. And then I said, I think the radius is 1/3. So I put 1/3 and -1/3. Now right now it doesn't look like it converges to either of those. But as we add more and more terms, look what happens, right? That -1/3 happens pretty fast, and then the positive 1/3 is oscillating, right, back and forth. But either way, it's not growing outside of those two lines. So that's a really nice way to say, yeah, I'm pretty sure it's a radius of 1/3. All right, so now that we've found our radius, what else do we need to do? Let's see, let h of x be defined below. Write the 5th degree Maclaurin polynomial. Okay, well, what is h of x? Well, it tells us that h of x is the antiderivative, or the integral, of f of t dt from 0 to x. Okay, well, do I have f of t anywhere? F of t, oh, I have f of x up here. And let's examine that, because they asked for the 5th degree Maclaurin, and looking at this, that only goes to the 4th. But if we envision an antiderivative here, isn't that going to be a 5th power? So what I'm going to suggest we do is we take this guy right here and find the antiderivative of it. So here's how I'd set this up. We would start with the fact that h of x is equal to the integral from 0 to x of f of t dt. Then we'll extend this out, and we'll say that's the integral from 0 to x, and let's sub in f of t dt. Now, up here it's not f of t, it's of x, but we're going to change the x's to t's just to make sure it matches our integration variables. So -1 plus 2x minus x squared, like so. Then we had two more terms at the end, 1/5 x cubed, 1/2 x to the 4th. Okay, and then technically it continues out, and I'm just going to do that to show that it doesn't stop. But I think that's all we're going to need. Let's make sure we remember how to do our antiderivatives. We keep our limits of integration there, and then we just start going through. -1x plus x squared minus 1/3 x cubed. And then, 1/5 x cubed is going to be x to the 4th, positive x to the 4th. That would be an extra 1/4 that'll combine with the 1/5 to make 1/20th. I'll give myself a little more room for clarity. And of course, I said I was going to change it to t, and then I promptly did not. I'm pretty confident you'd be fine on the AP exam if you didn't do it, but you probably should do it right in your notes. Right, Mr. Grant? Yeah, there we go. Awesome. So then 1/2 t to the 4th is going to be minus, there's going to be a t to the 5th there, so we know it's going to be a 1/5, and 1/2 makes 1/10. There we go. And then, of course, we need to substitute in our endpoints. When you replace the t's with x's, you get exactly what I just erased. Maybe. There we go. All right. X to the 4th minus 1/10 x to the 5th. And then when you substitute 0 in for all of this, right, 0 is just going to be 0 everywhere. So I'm going to show that it's minus 0. It is pretty optional, but that's about all we need. So what's our final answer? Well, I would stop there, I think. Because, yeah, technically there's more to this. However, they asked for the 5th degree, and I would argue that this is our 5th degree Maclaurin polynomial. Well, we just did integration, so it makes sense that derivatives should follow. Write the first 4 non-zero terms of the Maclaurin series for g prime, the derivative of g, then express that as a rational function which represents the sum of the Maclaurin series. There's a lot there. We should probably take this one sentence at a time. So we're going to start with g prime of x, and to start with g prime of x, we should probably actually start with g of x. And g of x was given to us, which was just lovely, wasn't it? So we have x minus 3/2 x squared plus 3x cubed. So g of x equals x, then minus 3/2 x squared plus 3x cubed. But they're going to have us take the derivative of this, and they said they want 4 terms, and I only have 3. And taking the derivative is still going to just give us 3 terms. So we should probably find the 4th term really quickly. And that's not too hard to do because the problem gave us the general term, right? The general term was -3 to the n minus 1 over n times x to the n. And we want our next term to have the next power, the 4th power. So I think that means that n is going to be 4. So we have x to the 4th, 4 negative 3 to the 4 minus 1. So I'm seeing -3 cubed over 4 times x to the 4th. And cleaning that up a bit, that looks like -27/4 x to the 4th. All right, so we know our next term, -27/4 x to the 4th. Now let's take our derivative. And derivatives of Maclaurin series are just as easy as you'd expect. You just take the derivative of each term. So g prime of x, we'll have 1. The 2's cancel. What a pretty problem. Who wrote this? I hope it was me. 27, wait, no, 3 times 3 is 9. Awkward. 9x squared. 4's cancel, minus 27x cubed. And they just asked for the first 4 non-zero terms, so I think that's pretty good right there. However, what is the crazy second sentence saying? Express g prime of x as a rational function. Do you guys remember what a rational function is? Right, a rational function is just a fraction, and it's going to have some polynomial up top, like x cubed plus x squared plus whatever. It's going to have a polynomial on the bottom too, like -x cubed minus 7x, something like that. Now, how do we get from g prime of x to those two polynomials? Well, the key in this is actually the sum of the Maclaurin series. Now, there's actually only one summation formula you need to know. I always include telescoping, so you can argue there's two, but that's not on the AP exam. So the only sum you need to know is the sum of a geometric series. And that's that a over 1 minus r. Now, in order to do that, we need a geometric series. So let's examine this. Do we have a geometric series? Is there a way to get from 1 to negative 3x, from negative 3x to 9x squared, and so on and so forth, using the same ratio every time? Well, to get from 1 to negative 3x, I think you multiply by negative 3x. Is that consistent all the way through? It looks like it. Yeah, I think every time we multiply by negative 3x. That's good, because now we can find the sum of this series. We can say our sum is the first term, and I'll write it out for you, over 1 minus that common ratio. Well, the first term is 1, and the common ratio was negative 3x. So this actually simplifies to 1 over 1 plus 3x. Does that fit the form of a rational function? Sure. There's a polynomial up here, and there's a polynomial down there. And so we have found that there are two different ways we can represent g prime of x. One way is a little bit more tedious. It's this power series that goes on forever. But then the other way is actually just the really nice function 1 over 1 plus 3x, which is pretty cool, right? We took this crazy series, found its derivative, and said, wait, its derivative actually has a much easier way to be written. All right, let's move on to E. E wants us to find the first four non-zero terms of the Maclaurin series for e to the x. I'm going to stop right there because we know this. This was one of our key must-knows at the beginning of this video. We need to know e to the x. Right? E to the x is 1 plus x squared over 2 factorial. So technically over 0 factorial, 1 factorial, so on and so forth. But it's a pretty easy one. Like so. And they wanted the first four non-zero terms, so I think that would... I'll just kind of put my plus at the end here. I think that would be 1 plus x plus 1 half x squared plus 1/6 x cubed. 1, 2, 3, 4 terms. Great. Use the Maclaurin series for e of x to write the third degree Taylor polynomial for k of x equals e to the x times g of x. All right, we can do this. So we have k of x equals e to the x, good, times g of x. Well, we know the series expansions for each of these, so let's start filling them in. We have 1 plus x plus 1 half x squared plus 1/6 x cubed, and there is, of course, more. And then g of x, right, we had up above. G of x was given to us, that's the x minus 3 halves x squared plus 3x cubed, and I don't remember what happens next, minus 27/4 x to the fourth, and so on and so forth. Are we done? No, we need to group all of our like exponential terms together, I guess like exponents together. And to do that, we need to go out to the third degree. So we get to stop multiplying when we get past the third power. So what I like to do is just start with the first term of the first series, which in this case is 1, and I multiply 1 times each of these until I get past the third power. That's a second power, it's a third power, oh, that's a fourth, I don't need that guy. So I have x minus 3 halves x squared plus 3x cubed, done with 1. Then I move on to the next, I'm going to move on to x. X times x is x squared, that's allowed. X times x squared is x cubed, that's allowed. X times x cubed, that's x to the fourth, I don't need that one. So I have two more terms here. So I have x squared and minus 3 halves x cubed. And then we do the same thing for the next. So I take 1 half x squared times x, that's a cube. X squared times x squared, oh, that's already a fourth power, I'm done there. So 1 half x squared times x is 1 half x cubed. And last but not least, we would go through and we'd check x cubed, but x cubed times x is already x to the fourth. That's too big. So I have all 6 of my terms here. Now, what do we do at this point? Well, we group the like terms. Here's the easiest way to do it. All right, the easiest way is to say k of x equals, and then we just kind of go through our terms. We have x, okay, that's nice, done there. And then we have a couple x cubed or x squared terms. We have one here, another one here, I'll put the invisible one, and that's it. So the really fast, easy way to do it is always put a plus, and then put parentheses, and put your coefficients. Minus 3 halves plus 1, and say that's the coefficient for x squared. Let's try one more. All right, we have 3x cubed, negative 3 halves, and 1 half. So we could say, okay, well, that's going to be 3 minus 3 halves plus 1 half, and then x cubed. And that's it, you're done. So that is definitely allowed. However, many of your perfectionists will want to simplify that down. It's great in practice, but make sure you fight that urge on the AP exam. You don't want to miss silly points just for missing something on simplifying. But I would see this as x minus 1 half x squared, and then this looks like 2x cubed, I think. But as always, if I do make mistakes simplifying, you guys will let me know in the comments, and then I'll fix it further down the road. Or I'll just leave an overlay in the video saying, whoops. All right, let's go ahead and move on to F, right? We have FGH here, and that's the first of our question 6s that we're done with. Find these ones go pretty quickly. So the 5th degree Maclaurin series for sine of x about x equals 0. Well, this is one of those that we should know, so let's start with sine of x. Sine of x is going to be, sine of x we need to remember is an odd function, so we only have odd exponents, right? So we might think, oh, does it start with 1? Well, I'd put x to the 0th, and then if we're adding exponents, that'd be x squared, x to the 4th, x to the 6th, right? Those are even exponents. I know 0 isn't really classified as even or odd, but I count it as even in this case, so that's not the right one. So I think our first one we need to start with is x to the 1st. And then we always alternate, so we have minus x cubed, and your denominator is just the exponent with the factorial, plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial, and so on and so forth. But wait, they actually only asked for the 5th degree, so scratch that guy out and say, there we go. All right, what's next? Oh, j of x. J of x is going to be our sine of x function plus f of x. And you might remember that we found f of x earlier. It does ask for the 5th degree polynomial, which is a little annoying because for f of x we only went out to the 4th degree. But going one more term isn't bad because we know how to build this, right? So we have negative 1, and I'm just getting this from the very first problem. Just have it written down on the side for me so I don't have to keep flipping back and forth. 1/5 x cubed, and then I said that and then had to flip back anyways. Yeah, it's not 1/5 x, yeah, 1/5 x cubed, 1/2 x to the 4th. There we go, that's what I was missing. 1/2 x to the 4th. So we do need one more term here, but that's easy, right? We know how to build terms at this point. It's the 5th derivative at 0 over 5 factorial times x minus 0 to the 5th. Okay. As we go out a little bit further, we still have this j of x over here. I'm going to go ahead and put in that sine of x function from up above. So x minus 1/6 x cubed, and then 5 factorial. I'm actually not quite sure what that is, so we could go through and I'm sure add it out. But let's see, 5 factorial. Are we even going to need it? Yeah, I think we are. As you can just keep it as a factorial. Someone asked at some point, can you keep factorials? I think it's 120. We could work that out, of course. And you can just keep 1 over 5 factorial if you like, though. And then on the other side, negative 1 plus 2x minus x squared plus 1/5 x cubed, 1/2 x to the 4th. And then finishing this off, we actually find that the 5th derivative is 0 from the table, so this whole last term is 0. Oh, well, that's nice then. Awesome. Okay, last but not least, we need to combine like terms just like what we did before. I think I made these come out pretty nicely though. So as we go through, we're just going to kind of cross them out as we see them. So negative 1 is good. What x's do we see? 1x plus 2x. I see 3 x's. Are there any like terms coming up? We have, no, just 1x squared. That's nice. Okay, what about x cubes? We have negative 1/6 plus 1/5, and maybe you're just not feeling the fractions today, so we'll use our nice shortcut, like so. So those are taken care of. We have a minus 1/2 x to the 4th, and then plus 1/5 factorial x to the 5th. And that looks pretty good to me. Moving on. We need the value of g prime of 0 using the given Maclaurin series. This is a funny one because they wouldn't normally make this problem this easy, and I'll show you the way that they want you to do it. But then I'll actually give you two other options that are arguably much easier. So I'm going to go ahead and split my paper kind of into 3 sections here, kind of 1, 2, 3. The first option that you see a lot on the multiple choice and sometimes on the free response is they want you to use g of x. Right? And we know g of x, we've done it several times now, where our g of x was that x minus 3/2 x squared plus 3x cubed minus 27 over 4x to the 4th, and so on and so forth. Now, they want g prime of 0. So you have to think back of how did we build these terms? Well, this was built for us, but how do you build a Taylor series? Well, you build a Taylor series by doing g prime of 0, and I'll write it out down below, g prime of 0 over 1 factorial times x minus 0 to the 1st. Now, of course, you would change it depending on where you are. So if this was your third, it would be g triple prime of 0 over 3 factorial, so on and so forth. So which term in here was built using g prime? Well, that is the term that has the first power. Which term has the first power? Well, that's x to the 1st over here. So we know that this eventually simplified down to x to the 1st power. All right, well, let's clean this up a little bit. We have g prime of 0. We have 1. This is x to the 1st equals x to the 1st. I think you could probably divide both sides by x to the 1st. It's not relevant. And that leaves us with g prime of 0 equals, when you divide off anything by itself, equals 1. And so that's telling us then that g prime of 0 has a value of 1. Now, I mentioned there's a few options here, and you guys might have already spotted the second option. Option 2 is that earlier we found g prime of x. So we could just literally use the Maclaurin series for this, where g prime of x, a little bit more space, we'll need 2 lines, g prime of x was equal to 1 minus 3x, right? This was the one where we wrote the rational function for it, 27x cubed, and so on and so forth. Now, every term is going to have an x in this problem except for the very first one. So when I plug in 0, I'll get 1 minus 0 plus 0 minus 0, which, if it's zeros all the way down, is just going to give me 1. That's pretty quick. Arguably, there's even an easier way, because we actually wrote a rational function for g prime of x. We said series are cool and all, but we have a very easy way to do this. It's 1 over 1 plus 3x. And this says to find any derivative, we can just replace x with 0. That's 1 over 1 plus 3 times 0, 1 over 1 plus 0, which is 1. So 3 different ways to do this. They really would want you to use option 1. All 3 of these would receive full credit. Correct math receives full credit. But option 1 is a lot of times the way that they'll kind of pigeonhole you into doing it. They probably wouldn't give you these, and they'd want you to know how to analyze a term. All right, let's go ahead and get into our last one before we switch problems. Our last one is the one that scares students across the board. It's known that for all derivatives greater than 6, so that means 7 and up, right? I don't have my pen there, 7 and up. The value of the derivative, actually the absolute value of the derivative, is less than or equal to 6 factorial. Let p sub n of 1/10 represent the nth degree polynomial for f of x around x equals 0, period. Use the Lagrange error bound to show that. Well, a lot of words here. You really should focus in on the Lagrange error bound. However, I'll give you a little bit of background about what's happening. So let's break this down. We have p sub 6 of 1/10. So they're saying we wrote a polynomial out to the 6th degree, and then we replaced x with 1/10, and we got some number. Now, if you only go out to the 6th degree and f of x, right? F of x has an infinite number of terms, then there's a pretty good chance that p sub 6, only going out to the 6th degree, isn't going to give you the right answer. To get the right answer for f of x equals 1/10, you would actually have to have an infinite number of terms with 1/10 plugged in. And it's probably going to give you a different number. So let's say that p sub 6 of 1/10 was like 7, but the actual value was 8. Well, if you subtract these two, if you say p sub 6 of 1/10, right, minus f of 1/10, then you're subtracting what you found versus what the actual value was. And by subtracting those, you get your error. So this is our error, how much we are wrong by. Now you'll notice in the problem they gave you the absolute value over here, and that's so that if you switch the two, or if you get a negative value, it doesn't matter. We're going to assume error is always positive. Whether you're a little bit too high, a little bit too low, but if you're off by 1, you're off by 1. Now, what are they asking us to show? They're asking us to show that the amount we're wrong by is less than 1/7 millionth. Oof. Okay, well that seems like a crazy fraction. How do we do that? Well, the Lagrange error bound and the alternating series error bound work in a pretty similar fashion. The Lagrange error bound says that if you have a power series, then you take the next term that you didn't use for your approximation. So let's build that first. So we have p sub 6 out to the 6th degree. So the next term that we didn't use is the 7th term. So let's build the 7th term, and we'll just do it over on the side. So our 7th term would be f 7th derivative of 0 over 7 factorial times x minus 0 to the 7th. The zeros come from it being centered at 7. Now, we're actually going to go a step further here, and we're not just getting the general 7th degree term. We wanted to use that term to basically add on to the power series we've already done. And to do that, we would replace x with what we substituted in, which was 1/10. So if we wanted to go one term further, this would be the next term that we would add on. Now we're not actually going to find the 7th derivative. It's kind of irrelevant here. This is where we branch off to a theorem called Taylor's theorem. Yeah, the same guy that Taylor's series are named after. And Taylor's theorem says, whoa, whoa, whoa. Don't find the 7th derivative at 0. It says that there's actually a derivative, a 7th derivative, that if you get it perfectly right, then this term is the exact amount you're wrong by. And it actually turns out that the number we substitute in here, and we'll kind of update this as we go, the number we substitute in here, I'll call it z, that seems to be pretty common. That value of z is going to be in between the center, and I'll say less than or equal to z, and your x value. Now I kind of ran out of room here, so I'm going to bring the 1 over 7 factorial next to this, right? Just bringing it down, and then the 1/10 to the 7th over here. So they're saying, why don't you just pick the right value, z in this case, it's some number between the center and the x value, and then that's the exact amount you're wrong by. But you might be asking the question, how the heck would I know that? And the answer is, you wouldn't. So instead, if we wanted to use this term, we could say this term, instead of being the exact amount you're wrong by, what if we just found the biggest value of this derivative on this interval? And then that's the most you could be wrong by. So what you'll see often is you'll see something like f7 of z, the center is 0, don't know why I put a fraction, less than or equal to z, and then the x value we used is 1/10. And then this is 1 over 7 factorial, okay, and 1/10 to the 7th, which if we wanted to write that out, right, it'd be 1 over, and then 10 to the first is 10, to the second adds another 0, third, fourth, fifth, sixth, 7th. That's 1 over 10 million. And then what they'll probably do right here is they'll say the max of this guy. So you can put max in there if you want, not that big of a deal. But yeah, either way, they would maybe even write max on top of it. They don't really care where you put it. So this rate here is the Lagrange error bound. It's the next term. You use the same x value, but instead of finding the derivative, you find the maximum of the derivative. Now, I've never graded a Lagrange error bound question, and I don't know how much of a stickler they are on the notation here. My guess is you could probably just say the max of this and then fill it in. In this case in particular, as you're about to see, it's a really easy one. Because what they've really taken to doing recently is giving you the max value. And they did that up above. They said any derivative of x will always be less than or equal to 6 factorial as long as it's more than the 7th derivative. Well, that's pretty cool. So they said we wanted the max of our derivative on this interval, but we know the max of the derivative on any interval is just 6 factorial. And this is 1 over 7 factorial, which I'm going to be sneaky right now. 7 factorial is the same as 7 times 6 times 5 times 4 times 3 times 2 times 1. That's actually 7 times 6 factorial, right? This is all 6 factorial here. And then times 1 over 10 million. Okay. Does anything cancel? I'm pretty sure it does. And we end up with 1/7 times 1/10 millionth, which is 1 over 70 million. Now, what did we do here? Well, they wanted to show the Lagrange error bound was less than 1 over 7 million. And we actually showed that the most you can be wrong by is 1/70th million, 70 millionth. Yeah, it sounds weird. And so that's actually pretty darn accurate, right? They're saying if you use the 6th degree, the most you're going to be wrong by is like 0.00000, like not a lot at all, isn't it? And so all we would just do at the end is say this is less than the number they asked us. And it is certainly less, right? If you divide by a larger number, the fraction becomes smaller. Now, 2 concluding thoughts on this problem. Technically, you should apply absolute value around this, right? We should apply absolute value. Error is always about absolute value, so it's not a bad thing to put in there. You'd probably get away with this. I don't think it'd really worry. You don't really need to worry one way or another, and especially once you get to this step, everything's positive anyways, so you can drop it. The second thing that we get asked is, do you need to simplify this? Because up until this point, we've said, you don't need to simplify. You don't need to simplify. In this case, you kind of do. Not too far, but you need to convince the grader, the reader, we'll say with beyond a reasonable doubt that you know your values reduce to less than what they've asked you to do, right? And so if you just wrote this, right, or maybe I'll even give you something over on the side. Maybe you had 6 factorial times 1 over 7 factorial times 1/10 to the 7th, and you said, that's less than 7 million, I think. I don't know. It's probably a good shot to give, but they may require you to go a little bit further. And as you can see, the math was not too terrible to get down there, but you might have to go another step or two simplifying this side to really convince your reader that you know that that's less than 1/7 millionth. Now, there's no stated rule about how far you go. It's one of those unspoken rules. Usually, Lagrange error bound is worth 2 points, right? It's worth 1 point for just getting the general format, and then the second point for showing that this format is less than the value that you asked. So, hopefully that was a decent explanation of the Lagrange error bound. I'd really suggest you take a quick pause point before you move on to the second question. The second question is faster than the first, and we're just going to touch on a few other things, but it's not a bad idea to take a brain break. So, once you're done with your brain break, unpause, and we will continue. All right, we've had that brain break, so let's go ahead and look into our last question 6, or question 6, part 2. So we're given f of x and g of x, and they're going to ask us a few questions about those. First, state the conditions necessary to use the integral test to determine the convergence of the series below. Okay, then use the integral test to show that the series below converges. That makes sense? Let's begin. The way the integral test works is we want to go through and we want to take the integral from x equals 0 to infinity of 1 over a function of x, so e to the x dx. And the reason we switch it to x's is because n's, or these series, these sequences, are defined as to not be able to use fractions or decimals for those n values, right? We just go straight from n to infinity, and we can't take the integral of just individual points. There wouldn't be any area. So instead we say, let's look at the integral of an actual function. But in order to do that, we need three things to happen. We need our function of 1 over e to the x to be, we'll say, is continuous. And I'm pretty sure e to the x is continuous. There's nothing that breaks this. And e to the x can never become 0. So we're never dividing by 0. That looks pretty good. We also need this to be positive. And I think if you ponder about exponents, you'll see that it's positive. Any exponent just moves e to the x above or below on the fraction. It never makes it negative. And then we also need this to be decreasing. And e to the x, or 1 over e to the x, is decreasing, right? 1 is a constant, and e to the x is getting bigger and bigger and bigger. And as the denominator of a fraction increases, the overall fraction decreases, in fact, to 0. So we can apply the integral test. Here we go. How do we do that? Well, the first thing is, of course, we work on that notation. And notation-wise is going to be the limit as b goes to infinity, right? We can't actually substitute in infinity. That's frowned upon. 1 over e to the x dx. And honestly, I probably should have done 2 steps in one. I don't want to run out of room here. But we're going to go 0 to b. I'm going to move e to the x to the numerator, so it's e to the negative x. So it's a little bit easier to take the antiderivative. In fact, speaking of, let's keep our limit and let's take the antiderivative. N approaches infinity. I don't know why I switched to n here. Awkward. B approaches infinity. And we end up with itself. But if you take the derivative, there'd be an extra -1 from the derivative of the power. And we need to cancel that out from 0 to b. And then I'm going to factor that -1 out. I hate dealing with extra negatives in there. It makes things just confusing for me. And then we're going to go through and substitute in 2 values. First, I'm going to substitute in b. So I'll bring the limit to come track down with that, because as b approaches infinity, we're substituting in b. It might as well have the limit associated with the variable we care about, minus, and then we substitute in 0. All right, don't need the limit there because it's not relevant to 0. All right, we end up with -1. And then in order to understand the limit as b approaches infinity, if you have a really good understanding of exponentials, you'd be all right. But otherwise, I'm going to rewrite this as 1 over e to the b. Good, and then anything to the 0th is 1. And hopefully now we can see that this becomes infinity, the entire denominator becomes infinity, and if you split $1 amongst an infinite number of people, well, they pretty much all get nothing. -1 times -1 is 1. Now, we should remember we didn't find the sum of the series, we just showed something. We showed that the integral of the function is finite. It comes out to be a value, and if that is the case, then the summation also comes out to convergence. So we need a quick summary. I would just say something like, therefore, the sum from n equals 0 to infinity of 1 over e to the n converges by the integral test. Nice. All right. Here we go. I do apologize because I did not give you nearly enough room on part B, and in the future I'll be better. Hopefully you're already watching an upgraded version of this video where you have a lot more room, because this is going to take quite a bit of room. These absolute convergences aren't usually that terrible, but the problem is we have to do 2 different tests here. So I'm going to split my paper in half, and we'll talk about the 2 tests that we need to do. In order to show absolute convergence, the first thing we do is we look at this and we say, okay, well, does the original one converge? So my original, I'll call it my OG over here, is the summation from n equals 0 to infinity of -1 to the n over 2e to the n plus 3. Now, they actually say use the limit comparison test here, but I don't think we need the limit comparison test at the beginning. I actually tried to do it at the beginning because I wasn't really thinking very clearly, and I'll show you what I ran into in just a second. But Do you see why you don't need the limit comparison test? As soon as you see that alternating factor, you should be thinking everyone's favorite test, which is the alternating series test. There's not too much we have to do with this. First, you have to ask yourself, does the series alternate in sign? Yeah, it's -1 to the n, right? So my series alternates. Okay. And then we really just have 2 more questions to answer. Okay. The next question is 1 over 2e to the n plus 3. Is that decreasing? Sure, the denominator is growing, so we would say that decreases. Okay. And we do need this to actually go to 0. So I'm going to quickly say the limit as n approaches infinity, 1 over 2e to the n plus 3. That will be 0 for the same reasoning as the previous problem, right? The whole denominator becomes infinitely large and we get 0. Therefore, converges by alternating series test. All right, does it alternate? Does it decrease? Does the limit go to 0? Great. However, all we showed is that the original function converges, and the stronger criterion for convergence is the absolute convergence. And the absolute convergence is cool, we found the original one converges, but what about the absolute value of the original one? And so what we're going to look at over here is, I'm just going to say the absolute value. We're going to look at the summation from n equals 0 to infinity of the absolute value, -1 to the n over 2e to the n plus 3. Okay. Now this denominator is always positive, so the absolute value is not doing anything to that. It's always positive, and our n's will only be positive. But the numerator is going to get really canceled out here because the absolute value of -1 is just always 1. And so we're left with 1 over 2e to the n plus 3. And now we have to prove that this summation also converges. And that is a little bit more challenging. Right? You might look at this and say, well, this is pretty similar if we take away our constants to 1 over e to the n. So I bet it is going to converge. And you're right, adding constants like that won't change it for the most part. But that's not enough to convince the readers. Now, this is where the limit comparison test comes in. The way the limit comparison test works is it says, take a series that you know. And guess what? In part A, we have a series that we know. It's this guy. And they said, and compare it to the series that you're trying to find convergence for. Now, what we're going to do here is we're going to take the limit of the quotient of the two of these. So we're going to take the limit as n approaches infinity of the quotient. And so basically what we're doing is we're going out infinitely far. And we're going to say, if these two series are still close to each other at infinity, then the values are pretty similar, and when you divide those values, it should come out to be a number. However, if they're really far apart and you divide them, then our answer is going to be infinity. So it doesn't matter whether you divide 2 over 3 or 3 over 2, that's still a value, which means it doesn't matter the order you set these up. I'll just take the new one we're looking at, which is 1 over 2e to the n plus 3, and then the old one, which is 1 over e to the n. And again, you can switch that order. What we're trying to do is we're trying to take this limit and see if we get an actual value. Okay, so let's do that. We get the limit as n approaches infinity. We'll do our normal flip thing. We end up with e to the n over 2e to the n plus 3. And we know limits are equal, now that we're dealing with limits, even ignoring a constant. And the e to the n's cancel, and that leaves us with 1/2. So what this tells us is if you go out infinitely far along the spectrum, your two different series, when you divide the corresponding term, you'll get 1/2, which means they're very close to each other. One's half as large as the other, if you will. But as long as this comes out to be a number, right? We say as long as our answer is between 0 and infinity, then we have a connection between the two series. What is the connection? Well, the connection is because they're close, they share that same convergence behavior. If one diverges, then the other diverges. If one converges, the other converges. So we would say something like, as the summation from n equals 0 to infinity of 1 over e to the n converges, we proved that in A, then the limit comparison test proves the summation from 0 to infinity of 1 over 2e to the n plus 3 converges. But wait, we're not done yet. I spelled converges wrong. That's not the reason why we're not done, though. We're not done yet because we didn't answer the question. It said, show that the series below converges absolutely. You showed the original series converges. You showed the absolute value converges. But what's our conclusion here? Well, then we would say, therefore, the series n equals 0. My summations are getting worse and worse. Negative 1 to the n over 2e to the n plus 3 converges absolutely. Right? Those are the two criteria you need to show for absolute convergence. The original converges and the absolute value converges. Don't forget your conclusion. Again, sorry about the room. I'm going to change that up, but hopefully by the time that you guys are working through this. Whew, okay, A and B done. We still have C, D, E, and F, but these ones go much faster. So here we go. First two terms of the series below are used to approximate g of 1. Well, let's actually see what that looks like really quickly. So g of 1 will be the first two terms. The first term is 0 substituted in, negative 1 to the 0th over 2e to the 0th plus 3. That's my first term. Plus negative 1 to the first over 2e to the first plus 3. So they're saying this is g of 1. Now, that's not g of 1, probably, because g of 1 is every single term, an infinite amount, right? This you could clean up if you wanted. This would be 1 over 2 plus 3, which is 5, minus 1 over 2e plus 3. Some value. Great. But that is probably not the right value. So their question is, use the alternating series error bound to see how much you could be wrong by. Well, there's a nice little proof in a previous video that says if your series is alternating in sign, look at that, alternating in sign, then all you need to do is find the very next term you didn't use, and that is the most you can be wrong by. So let's find the next term. This first term was created by using n equals 0. This second term was created by using n equals 1. So I need the term that's created by using n equals 2. That will be negative 1 squared over 2e to the second plus 3. And technically, we should probably apply absolute value because error can be is always positive. Now, we'll find that isn't going to matter in about 5 seconds because negative 1 squared is 1. And then this is 2e squared plus 3, right? So we don't really even need the absolute value because that's already positive. What did we just find, though? We found that this is the most we can be wrong by, right? So our sum, g of 1, our approximation, so we could say g of 1 that was approximated, right, by this 1/5 minus 1 over 2e plus 3, right, is only wrong by, so my error, my max error, is 1 over 2e squared plus 3. That's pretty small, right? E squared, 2 point something, we'll call it 5 times 2 is 10, 13. You're only wrong by 1/13, and you only use 2 terms. The more terms you use, the more accurate you get. Great. Part D. Let j be the function j of x equals f of negative 2x. Find the first 3 terms and the general term for the Maclaurin series. Okay, now we get to move faster. So j of x is equal to f of negative 2x. Let's do a little sidebar over here, and let's talk about just f of x, just so we don't forget it. Right? They gave us f of x at the beginning of this problem. They said f of x was x over 3, x squared over 4, x cubed over 5, plus x to the n over n plus 2. All right, well, to find f of negative 2x, right, they are just taking the x's that are in here and replacing them with negative 2x's. That's our function notation. So we're going to have negative 2x plus negative 2x plus negative 2x. I'll fill in the blanks in just a second. Negative 2x. Then I'll do the rest in purple to match my series. Over 3, over 4, over 5, and this is to the nth over n plus 2. And we're pretty much set. Oops, I forgot my square and cube. Awkward. I'm going to quickly rewrite this just because it makes me happier, just to kind of pull everything out here where I see negative 2/3 x. Negative 2 squared is 4. 4 over 4 is 1, so that's just x. This is negative 8/5 x cubed. And then I'll clean this up just a little bit too. There's nothing too much that you have to do here. I'm going to distribute the n, and I just really like to write the x to the n term by itself. So I have negative 2 to the n over n plus 2. And then I'll put the x to the n at the end. And I like doing that so you can see the format of the power series. It shows us this is centered at 0. We see the x to the n format. Pretty nice. And that's it. All right, let's take a look at E here. So E was kind, and they gave us the Maclaurin series for the natural log of 1 plus x, which means if you graph all of this on Desmos, it should look identical to this graph. And they've said, now we have a new function h, and h is x times the natural log of 1 plus x over 3. And they want the first 4 non-zero terms and then the general term of the Maclaurin series. Now, the long way to do this would be to take h of x, and then you would find h prime of x and h double prime of x, using the product rule and the chain rule all the way through h triple prime of x. And then you could use all of those to write the Maclaurin series. Or we could take what's already given to us and manipulate that to create h of x. So let's start. We know that h of x is x times, and then the natural log of 1 plus x over 3. So actually, let's take a brief interlude here, and let's look at the natural log of 1 plus x over 3, and I'll probably do that right over here. We can just kind of split this in half. So we have the natural log of 1 plus x, which was that x minus x squared over 2 plus x cubed over 3. It's actually a pretty nice Maclaurin series, right? Plus dot 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 plus negative 1 to the n plus 1. I'm using my infinite paper. Whoopsies. X to the n over n. Okay. Now, let's convert that x to an x plus, or an x over 3. And we're allowed to do this. We're allowed to substitute in division or multiplication by x. Earlier we did a negative 2x. Here we're doing it divided by 3. We're allowed to do that. We couldn't do something like x plus 1 in for x. That wouldn't work as well. That would change the center of the series over here, but x over 3 will not. So all I'm going to do is take every one of my x's, and I'm just going to leave some space here. And in fact, let's go ahead and do this. Let's do 1/2 x squared plus 1/3 x cubed minus 1/4 x to the 4th. Oops, that wasn't it. X to the 4th. And then we have this plus negative 1 to the n plus 1 times 1 over n times x to the n. There we go. And all we're going to do is we're going to take every single one of these x's in here, and we're going to replace them all with x over 3, which isn't too terrible. And so that is the Maclaurin series for the natural log of 1 plus x over 3. Now, we do need to fit that in with a times x out front, and so actually I should probably redo this and maybe give us all a little bit more space next year. I'm always better next year. So we have our x times, and then let's do a big set of parentheses over here, and then I'll start simplifying in the natural log of 1 plus x over 3. So we have 1/3 x. That's pretty good. Now this guy, a little bit of math here, right? We have 3 squared, which is 9. 9 times 2, which is 18. So I have minus 1/18 x squared. Okay, and then we'll just keep going through, right? So our next one is going to be, well, we have 3 cubed, which is 27, and then 27 times another 3 is 81. So plus 1 over 81 x cubed. And then we have a minus, and this one will be the trickiest of all because 3 to the 4th, I think, is 81 times an extra 4 is going to be 324. So 1 over 324 x to the 4th. And then, of course, our general term. The general term plus dot 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 negative 1 to the n plus 1 times, very much out of space. We have 3 to the n times 1 over n. So 1 over n times 3 to the n, and then x to the n. Now again, you don't have to write it that way, but I really am fond of keeping the x to the n, that's supposed to be an n, separate so you can see that it's centered, in this case, at 0. Now we're still not quite done because I have this x out front, and I will, of course, need to distribute the x to everything in here. So this to me is looking like a final Maclaurin series of 1/3 x squared minus 1/18 x cubed, 1/81 x to the 4th, 1/324 x to the 5th, and then we have negative 1 to the n plus 1. I'm going to get rid of this because that's just getting messy here, times 1. Maybe we'll move all that to the top of the fraction and save some space. Take that. Over, right, and then what was it? We had all the way out there, n times 3 to the n. There we go. Old age is getting to me. And then we have x to the n times another x. Same base, add the exponents. That's going to be n plus 1. And I think we should be set. You could pretty quickly check this by graphing this equation and then graphing this one and making sure that they look pretty similar, and hopefully they do. All right. Next up, we have F, which says find the interval of convergence. This is another one that I do apologize. I really should have done a better job of giving you space for, but hindsight, it'll be better hopefully after recording this video. So let's go ahead and begin. We need the interval of convergence. Before we get the interval of convergence, we actually need to find the radius of convergence. So again, we have that same power series as up above, and we're going to take the general term, and we are going to use the ratio test, which we covered earlier in this video. The limit as n approaches infinity. We have that absolute value. We have this complex fraction, and negative 1 to the n. And we're replacing n here, aren't we? So it's going to be n plus 1 times x to the n plus 1 all over n plus 1. You could keep it separate like we did here, but I figured it was easier to see two fraction lines. And then the denominator, of course, was negative 1 to the n plus 1. It's just the nth term, which is given to us, x to the n over n. Right. Let's multiply by the reciprocal here. So limit as n approaches infinity. This is where we need that kind of long fraction line. And then the numerator and denominator should each contain one of the unique terms. So if this guy ends up in the numerator, then this one will end up in the denominator. There's always that kind of give and take. So I have negative 1 to the n plus 2 times x to the n times x to the first. I'm going to go ahead and split that, might as well. And then what else is going to come up? There's going to be an n up there as well. Maybe I can color coordinate. There we go. And then we need the denominator. There was, of course, an n plus 1. I'm going to line that up with the n over here just to save some time. And then, of course, we have our negative 1 to the n plus 1 and our x to the n. Now, looking at all of this, these are either negative 1 or positive 1. It doesn't really matter because they're inside the absolute value, so all they're going to do is just turn to 1, which means we can pretty much neglect those. It makes no difference at all. We certainly can cancel out those x to the n's, and so what I'm really seeing at this point is the limit as n approaches infinity of the absolute value, and then I'll do that same split, n over n plus 1, so taking this guy as one part, these are essentially gone, and we end up with an extra x over here. All right, then let's go ahead and actually apply the limit. We look at the coefficients, ignore that extra small little constant, and we say anything by itself is 1. So I'm seeing 1 times x, or just the absolute value of x. Now we're not done here because the whole point of the ratio test is we need our ratio to always be less than 1. Otherwise, it won't be a convergent geometric series. Geometric series converge with r less than 1. So we have that. All right, things are looking pretty good so far, but we're not done yet. Because although we know that the radius is 1, right, and because this is x minus 0, we know that the center is 0. We don't know the full interval. So if we start at 0, we are allowed to go 1 in each direction. And so the way that we can write this using our inequalities is we are centered at x, or x minus 0 is probably a better way to think about it. That's going to be less than 1, which is less than negative 1, right? We take the radius, use the positive, use the negative. That's how our absolute value inequalities will always work. And then I really don't need the x minus 0, so I'm going to just kind of put my final answer down here with a less than x, less than 1. So it's telling us we can use any x that's less than, that's greater than negative 1, less than positive 1. But sometimes you can include the endpoints. Right? The endpoints are the only points on this interval of convergence that can be conditionally convergent, and so we do have to check them. And to check them, we're just going to make 2 columns here, and we're going to check each one. So I'll go ahead and check, do this just to make sure we know where we are. I'm going to go ahead and check x equals negative 1 here, and x equals positive 1 on the right side, but we'll start with negative 1. With negative 1, we go through and we replace, or we take our general term, we write it with a summation, okay, and we say we are summing this general term up from n equals something to infinity. And then here's our general term, negative 1 to the n plus 1 times no longer x. We now know x is negative 1, so negative 1 to the n over n. Where do we start? Well, if you look at the general term, this is x to the first power, so I'd argue we're actually starting at an x of, or an n of 1. It doesn't particularly matter. 1 or 0 isn't going to change anything. But what we do need to do is clean this guy up. Now, this can get a little bit tricky here. I'm going to go that same route of same base, add the exponents. There's probably a better way to do this, but that's what I'm treating this with. So we're going from n equals 1 to infinity. Same base, so we're going to combine the exponents together, n plus 1 plus n, right, over n. Now, we should be able to see that that goes to 2n plus 1, but we need a quick discussion about 2n plus 1. So if I have 2n plus 1, let's see what happens to this exponent for the first few n values. So let's see, n equals 1, n equals 2, n equals 3. If n equals 1, we double it, so it becomes 2 times 1 plus 1. So you double it, so it's an even number. And then you add 1, that makes it an odd number. For the next one, you double it, it's even, add 1, it's odd. Same thing, double it, it's even, add 1, it's odd. So actually this exponent of 2n plus 1 that's up here, maybe I'll write that for clarity, 2n plus 1 is always odd. So what happens when you take negative 1 to an always odd power? Can you see it? Negative 1 to an odd power is just negative 1 every single time. So actually I'm going to quickly rewrite this as from 1 to infinity of just negative 1. I'm getting rid of the exponent because it's always negative 1 times 1 over n, right? That's the over n part that we have here. And in fact, because that's a constant, let's factor that out really quickly. Let's get the sum n equals 1 to infinity of just 1 over n. And what do we know about the convergence of this? That's the harmonic series. So we're going to say harmonic series, which means diverges. Right? Remember that a constant out front can't affect convergence or divergence, so you could argue maybe it's the negative harmonic series, right? Negative 1 over 1, negative 1 over 2, but it still diverges, just diverges at negative infinity instead of positive. All right, let's look at our last one, x equals positive 1. So we're going to have the summation from n equals 1 to infinity, negative 1 to the n plus 1 again, right? And then we're taking x and we're replacing it with 1. So it's 1 to the n over n. And as we go through here, 1 to any power is just 1. So I'm pretty sure that this is just n equals 1 to infinity of negative 1 to the n plus 1 times 1 over n. Now, this power is going to alternate or oscillate every time. Negative, positive, negative, positive. Try a few values of n if you're not sure. which means then that 1 over n is negative, positive, and so we know something about that. That means that this series converges. Why does it converge? Because this is the alternating harmonic series. So when x is 1, our series converges, which means we're allowed to include x equals 1 on our interval of convergence, but we're not allowed to use x equals negative 1. And there we go. We have our final interval of convergence. Now, in this video, I really tried to go through and cover most, if not all, of the questions that they'll ask you about series. They can, of course, ask these in different ways. They can ask you with graphs, they can ask you with more tables, and the only way to really get good at it is pull the last 10, 20 years of questions and just do question 6, right? Do one a day. So spend 15 minutes a day on question 6. And that means when you walk into your exam in a couple weeks or whenever it's going to be, you're not surprised by question 6. You're like, oh, they're asking about where you substitute in a value for x. Oh, they're asking about the interval of convergence. They're pretty straightforward questions, but they can look really intimidating with all that sigma notation. There are a couple specific types of questions that they do like to ask on the multiple choice that don't come up as much on the free response. And I think I have a previous video on some of those problems. Look in my power series section, but if I don't, just let me know and I can always throw one up there. So hopefully this was pretty helpful on what can potentially be a scary topic. I really do believe that this can actually be one of the easier free responses, and I would actually suggest you don't save it to the end, right? This is in the 4 free response section. This is section 2, part B. So you're going to do free responses 3, 4, 5, and 6. I'd really suggest you skip to question 6 first and get it out of the way, right? Either you're conquering your fear or you're attacking something that you feel confident on, right? Get that out of the way, then try the rest. This is the predictable one. You can do it. Thanks for tuning in, and hopefully this was helpful.